All right, gentlemen, let's continue. So, in this video, we will talk about solutions about ordinary points. Okay. We will start first with the definition. Okay. Again, now we will focus on solving second order linear differential equation. Here, mainly the coefficients are not constants. Okay. So we know that the general form of second order linear differential equation is this a sub 2. Here we have x times y double prime. That's our function, unknown function, right? And a sub 1 of x, y sub y prime plus a sub 0 of x, y is equal to 0. Okay. And also we know that by dividing both sides by a sub 2, this leading coefficient, we can just change this or reduce this to this form, which is called the standard form of the second order linear differential equation, right? And here we know that this p is equal to a sub 1 over a sub 2, and here a sub 0 equal q is equal to a sub 0 over a sub 2. Okay. And also here, primarily in these examples, we are interested in the differential equations where these coefficients, this a sub 2, a sub 1, and a sub 0, these are polynomial functions, okay? When it is not polynomial, also we will see some examples, okay, like for example, a sub 2 may be sine of x, y double prime plus y prime equals 0, or here we have y double prime, and here we have maybe cosine of x, or we have e to the power x, something like that. Okay, so let's start with this definition. Ordinary and singular points. Okay, so a point x equals 0, x equals x sub 0 is said to be an ordinary point of the differential equation, not differential equation 1. So that is 1, right? This one is the first one. If both coefficients, that's b, okay, here we have 1. All right, I think there must be, okay, all right, got it. Let's just give me a second. Okay. So a point x equals x sub 0 is some point is said to be an ordinary point of the differential equation. Okay, I'll correct this later. That is our first equation, and the second equation, if both coefficients p of x and q of x in the standard form 2 are analytic at x sub 0. A point that is not an ordinary point of 1 is said to be a singular point of the differential equation. Okay, so what do we mean by analytic at x sub 0? All right. So it says that if both coefficients, this p of x and q of x in the standard form, that means after we bring this standard form, okay, these are analytic at x sub 0 means simply this p of x, it has power series representation about this point. Simply it means this. That means that I can just find a power series representation which is n equals 0 to positive infinity. Here we have a sub n times x minus x sub 0 to the power n. Okay, so that is, these are analytic at x sub 0 means this. It means that these functions have power series solutions, representation about the point x sub 0. And also x sub 0, as you know, it is maybe here somewhere, okay? That is our function, all right? And maybe it's a bit complicated function. We are trying to find this power series representation. From this point, we start our approximation, right? First draw a straight line, maybe first quadratic function, then cubic function. As you know, as you add more and more terms, it gives us better and better approximation. Okay. So how about this q? Also q for the same thing. Also q of x is analytic at this point. X sub 0 means also it has power series representation. That q of x, I can write it as sigma here. We have n is equal to 0 to positive infinity. Here we have c sub n, x minus x sub 0 to the power n. Okay. This is what we mean by analytic at x sub 0. Simply, we can just find their power series representation. A point that is not an ordinary point of 1 is said to be a singular point of the differential equation. Okay? Some functions at some point we cannot find. Now we will see some examples. For example, if I have the function here, let's say 1 over x. At sub 0, when x is equal to 0, it doesn't have power series representation. Why? Because 1 over x at 0, we cannot actually, how to say, we cannot determine its value, right? Because it is not defined. Okay, some examples. Consider the following equations. Okay, I mean, what points are ordinary points? What points are different singular points of these equations? If you just consider the first one, we have two here, for example, a part 1, y double prime plus y is equal to 0, right? It is already in standard form. What we have here? Here we have y double prime plus 0 times y prime plus 1 times y is equal to 0. And here we have, what is our p? P of x is equal to 0 and q of x is equal to 1. They're already polynomial function, right? I can just write it as something like this: 0 plus 0 times x plus 0 times x squared. It has actually, it is analytic at 0 or any point. How about this one? Also, it's already polynomial function. I can write it as 1 plus 0 times x plus 0 times x squared. So it has also power series representation. So these two functions are, what is it? Analytic, not at 0, at anywhere, right? So actually that means that here, this P and Q, they are always analytic at any point on the number line. So they don't, it doesn't have any singular point. How about second one? In similar way, y double prime plus 3y prime plus 2y is equal to 0. Here, what is p? Our p is 3, and how about q? Q of x is equal to 2. Also, actually, it's a polynomial function, right? Just actually one constant term, but degree is 0, but also it's polynomial function. And also this thing, right? And also I can find the power series solution. What is it? It's just 2 plus 0 times x plus 0 times x squared, right? So that means they're analytic at any point on the number line. How about here in question B, y double prime plus e to the power x y prime plus sine of x, right? And y is equal to 0. And here it's already in standard form. So p of x is equal to e to the power x. We have just actually studied that it has power series representation, right? And the q is equal to sine of x, and also it has power series representation. That means that these functions, they are analytic at any point on the number line. That means that they do not have any singular point. Okay, that is examples for ordinary points. Okay, any point on the number line, they are ordinary points for P and Q for all of these examples. How about in this example, singular points? Okay, question A, question B. So here in question A, It's already in standard form, right? Because the coefficient of y double prime is 1. And here, if you recognize P is equal to X, right? And how about Q? Our Q is natural logarithm of X. Okay. So it's already a polynomial function. We have no problem. It is analytic at any point on the number line, right? Once again, I can just write it as 0 plus 1 times x plus 0 times x squared, right? And how about natural logarithm of x? And we know that this function, right, it doesn't have power series representation when x equals 0 or x equals less than 0, right? So that means that, for example, this x sub 0 is equal to 0. That is, it is singular point. That means that around or above this point, we cannot find it is power series representation. Actually, any point that is less than 0, that is a singular point, right? Why? Because if you try to find this, differentiate this, if you differentiate this, we will have 1 over x. When you are, for example, trying to find the Taylor series expansion of this function, we cannot evaluate this, right? And also 0 is not defined here, and that's why these 2 points and any negative number or 0, it is a singular point for natural logarithm of x. That means that at this point we cannot find it is power series representation of this differential equation. But any point that is greater than 0, actually that is ordinary point for natural logarithm of x. Okay, we are just considering these examples, and after that we will draw a conclusion and we will give it as a theorem. How about in this example B? First, we have to write it in standard form. If you divide both sides by x, so here we have y double prime plus 1 over x y prime plus y is equal to 0. So here we have p of x is equal to 1 over x and q of x is equal to 1. Right? That is our p, this is our q. And with this, we have no problem. It is analytic at any point. The problem is here. Right? So what is the singular point? Does it have any singular point? Yes. What is it? That x sub 0 equals 0. That is the singular point. Okay. And because near 0, this function behaves very badly. Okay. That's why we cannot find, or we cannot find it is power series representation above this point. But any point except for 0, it is ordinary point. So it has power series representation, or it's just simply analytic. Okay? Because of here, because 1 over x, you cannot calculate the value of this function here. Okay? Because it's all about Taylor series. You know, when you just find it is p of x, Taylor series at 0, for example, that's Maclaurin series. What we have here? Here we have p of 0, right? And here we have p prime of 0 over 1 factorial. Here we have x, right, plus p double prime of 0 over 2 factorial, x squared, dot, dot, right? Now, if you evaluate this, what is the derivative of this function? Minus 1 over x squared, right? So here we have minus 1 over x squared. This thing is, here we have 1 over 0. Can I evaluate this value here? We cannot. And that's why actually it doesn't have power series representation. That's why we are saying that that is singular point. Okay? All right. So polynomial coefficients. So we will primarily interested in the case when the coefficient that a sub 2 of x, a sub 1 of x, and a sub 0 of x in our first equation, that is our second order linear differential equation, they are all polynomial functions with no common factors. Also, it makes sense because if we have common factors, right? And let's say this x minus x sub 0 is a common factor, I can just take it out and still I can just write it in such a way that these two polynomial functions, a sub 2, a sub 1, and a sub 0, so that they do not have any common factor. Okay, so a polynomial function is analytic at any value of x, as we know, because polynomial, we don't have any x in the denominator, so we have no problem. As you know, polynomial functions are really good functions. We can differentiate this very easily. We can integrate them very easily, right? And that's why mathematicians were interested in finding this power series representation of the function. Power series means it's just polynomial function, but we have infinitely many terms. So, and a rational function is analytic except at points where its denominator is 0. And also from calculus, you know that what is a rational function? It is just the quotient of, or the ratio of, two polynomial function, right? That is, what is it? It is P over Q. That is polynomial function. This is also polynomial function. So it's the ratio, we call this rational function. And we are saying that also that is analytic except where this denominator is equal to 0. And also, you know the reason, because we don't have 0 division, right? So that is, here we have P of x, that is a sub 2 over a sub 1, Q of x, a sub 0 and a sub 1. When this a sub 2, no, I think I made a mistake here. It should be a sub 1 over a sub 2. A sub 2 over a sub 0 over a sub 2. Okay. So here a sub 2 are analytic except at those numbers for which a sub 2 is not equal to 0. I mean, here, if a sub 2 is equal to 0, that is what is this, singular point, right? When a sub 2 is not equal to 0, actually they are all ordinary points and they have power series representations. That means that these functions are analytic. Okay, then we can give this very simple small theorem. A number x equals x sub 0 is an ordinary point of 1. That's our first differential equation. If a sub 2 of x sub 2, at this point, the value of this polynomial is not equal to 0. Then that is ordinary point. Otherwise, it is just singular point. Okay, if it's equal to 0, then it is a singular point. Okay. Ordinary and the singular points. That's the last example. And after that, we'll get back to our power series solutions of differential equation. Consider the following equations. Okay, the first one, a, using that thing here, what we have here, a sub 2 of x is equal to x squared minus 1, right? So what are the ordinary points and what numbers are the singular points? So actually, if is equal to 0, this gives us singular points, right? So here we have x equals 1 and x equals negative 1. And these are, what is it? Singular points. Singular points. So that means that if I'm trying to find the solution or power series solution of this differential equation, right? We should not find this about these 2 points. Okay, but you can choose any other points. We can choose like about 2 or 3 or any point, 0, but here not these points. These are singular points. Okay, that means that what should we understand from here? Assume that you need to solve this differential equation and you're trying to find it is power series solutions, right? And here it is saying that do not look for the solution of this differential equation in this form, that sigma n equals 0 to positive infinity. Here we have c sub n, x maybe plus or minus 1 to the power n. It's saying that do not look for the solution or do not assume that that can be the solution, right? Anything else is possible. We can find this solution. But if you try to find the solution of this differential equation in this form, then you'll just actually end up with dead end, all right? There's no escape. So you cannot find a solution. And that's why it's saying that these are singular points, all right? No solutions at these points. So stay away from these 2 points. That is what we are trying to understand from this. How about question B? In question B, here we have a sub 2 of x is equal to x sub 0, right? So that means that x equals 0 is, what is it? Singular point. Okay. Also, that means that if you remember in the first example, we assumed that the solution of the differential equation is, what is it? N equals 0 to the positive infinity, c sub n x to the power n, right? If you remember that y prime plus y is equal to 0, that's how we solve. But here, since x is equal to 0, right? And what we have here? Actually, here we have x to the power n means, here we have x minus 0 to the power n. Okay, this assumption does not work for this function. Okay, because this x equals 0, this thing is singular points. Okay, above this point, near this point, this differential equation do not have power series solutions of this form. Okay, that is not possible. Okay, that's what we understand from, I mean, why we are studying here singular and the ordinary points, that you should recognize and you should know the difference between these two things. Okay, now actually we'll give the theorem. So see the last problem. How about here? Also, it can be complex number f x. Let me rewrite this. Okay, so here we have a sub 2 of x is equal to x sub x squared plus 1, right? So when this is equal to 0, the solutions of this equation will be singular points. What are the solutions? We know that x is equal to plus minus I, right? So this is this plus I and minus I. These are, what is it? The singular points of this differential equation. Okay. Okay. So let's just give this theorem. It's all about actually this theorem. And we actually study those examples to understand or to obtain this theorem. So this theorem says that existence of power series solutions. Because now, okay, you are assuming that we are given a differential equation, and let's say second order linear differential equation. Now, in analytic way, we cannot find a solution. Now the second try is, how about it is power series solution? Now before trying this, we have to make sure that it has power series solution, right? So how do I know that it has power series solution or not? Number one, if yes, above which point? Because we should not look for the power series solutions of the differential equation about singular points, near the singular points, right? And that's why this theorem says that if x equals x sub 0 is an ordinary point of the differential equation 1, now we know what we mean by ordinary point, right? We can always find two linearly independent solutions in the form of a power series centered at x sub 0, because x sub 0 is not a singular point. It is an ordinary point. That is y is equal to c sub n, x minus x sub 0 to the power n. Okay. So what that is, that's one is if you're talking about this differential equation, that is y double prime plus a sub 1 of x y prime plus a sub 0 of x y is equal to 0. That's homogeneous, right? And if you know that actually if x sub 0 is not a singular point, that means that a sub 2 of x sub 0 is not equal to 0, then we can look for the solution, power series solution of this differential equation in this form, and it exists, and we can find two independent solutions. Okay, a power series solution converges at least on some interval defined by x minus x sub 0 less than or equal less than r, where r is the distance from x sub 0 to the closest singular point. And also we'll see this in example. Okay, so a solution of the form, that solution of the form is said to be a solution about the ordinary point x sub 0. Okay, and the distance r in theorem, this here, this r, the distance is the minimum value or lower bound for the radius of convergence. Okay, that's the convergence. We know also studied how to find this r. Now we will see them in example. Consider the following equation. It's about minimum radius of convergence. Okay, A. For example, let's find singular points here. That A sub 2, that's equal to x squared minus 1. So singular points are x equals plus minus 1, right? So that means that if I just draw our number line, that is our 0. Here we have -1. Here we have 1, right? At these points, actually, this differential equation do not have power series representation, power series solution. All right. So now, since it is x sub 0 right here, this x sub 0, what is it? Plus 1 and minus 1. These are what is it? Singular points, x equals 1 and x equals minus 1. These are singular points, right? And the minimum radius of convergence, right? Minimum radius of convergence at 1, what is it? It is this, right? And this thing. So that's x, right? Here we have this x less than, this means that less than 1, right? Because at this point, there's a singular point. This point is a singular point, right? And that is the radius because it's the center, right? And all the points between this, they are ordinary points, but that is the singular point. Okay. That means that we can choose any point between -1 and 1, but not -1 and 1. How about outside or -1 and outside 1? Also, actually, they are ordinary points. At the time, radius will be different. Okay, because here, the theorem, we are saying that a power series solution converges at least on some interval defined by x minus x sub 0 less than r, where r is a distance, from x sub 0 to the closest singular point. Okay, closed singular point, that is -1 and 1, right? So that's closest singular point is -1 and 1. How a question B, here we have x squared. So a sub 2 is equal to x squared. That is equal to 0. That means that x equals 0 is a singular point, right? So only it has singular points is equal to 0, and all other points are, what is this? Ordinary points. Okay. All right. That's all for today.